These seismic tables, both rigid and flexible analyses, have the same format as the wind tables. However, the height to width factor is different from the wind height to width factor as it not only applies to fiberboard. On the other hand, the unblocked structural wood panel factor will behave the same way. For seismic design, the height to width factor is based on the following table. Thus, if exceeding any of the maximum shear wall aspect ratios specified, zero force will be allocated to the wall or wall segment. Note 1 is for blocked wood structural panels concerning the aspect ratio, and in order for the wall to resist the seismic forces, the shear wall aspect ratio shall not exceed 2 to 1 unless the unit shear capacity is multiplied by the following factor, while not exceeding the maximum aspect ratio specified. Note 2 is the same as for wind design. For unblocked gypsum wallboard shear walls with an aspect ratio greater than 1.5 to 1, zero force will be allocated to the wall. Note 3 applies to structural fiberboard, and to resist the seismic forces, the aspect ratio shall not be greater than 1 to 1 unless it is multiplied by the seismic aspect ratio factor. It is worth mentioning that the behavior for both wind and seismic design may not be always observed when the include deflection analysis and the use shear wall deflection to calculate rigidity from the design tab in the setting options as shown earlier, since this is an iterative process, and for the program to achieve the same deflection throughout the wall, it sometimes has to allocate zero force to smaller, therefore less stiff segments compared to larger wall segments in order to converge. Therefore, it may be possible that zero force is allocated to a segment even though it conforms to the SPID-WIS requirements previously presented. Now back to the wind shear results table for flexible diaphragm design. To the right of the height to width ratio factors and unblocked structural wood factor CUB is the part of the table attributed to the description of the forces applied to the shear line, wall, or wall segment. V is a total force based on the allowable stress design. For a shear line, it is the total force applied to the shear line, and for a wall or wall segment, it is the total force applied to that wall or segment. To demonstrate this, we will select line A of level 1 and compare the force from the table and the one seen in the elevation view. The arrow to the left is the factored shear force, and as expected, it is the same as the one in the table. The term Vmax represents the base shear of the wall or segment based on the allowable stress design factored shear force per unit full height sheathing, including the perforation factor. The term V is simply the design shear force per unit full height sheathing that the wall must resist. Thus, it is the maximum force applied on the wall or wall segment. Vmax is always equal to V unless there is the presence of a perforated factor associated with the use of perforated walls with openings. The next section of the table is dedicated to the properties of the shear wall, in other words, the resistance of the shear wall. The first two terms, int and ext, represents the unit shear capacity of the interior and exterior sheathing, which takes into account the height to width factor and the unblocked factor, respectively. The term CO is the perforation factor obtained from SPID-WIS equation for perforated walls. Hence, unless not using perforated walls, the value should always be equal to 1. The perforation factor is a factor that reduces the nominal unit shear capacity of the shear wall based on the sheathing area ratio and the ratio of the total length of the shear wall to the sum of the individual perforated segments contributing to the shear resistance. The wall capacity is determined based on the lowest perforation factor. The total unit shear resistance of the shear wall, total, is determined by applying the SPID-WIS sheathing combination rule. Therefore, the resistance of the shear wall may not always be the summation of the interior and exterior capacity of the sheathing according to the following SPID-WIS clause. For example, for shear walls with dissimilar sheathing materials on opposite sides, the combined nominal unit shear capacity, represented by the letter X, is the greater of either 2 times the smaller nominal unit shear capacity or the larger nominal unit shear capacity. There is an exception to the previous rule, which is that for wind design, the combined capacity for shear walls composed of wood-based material on one side combined with gypsum wallboard is the sum of the two capacities represented by the letter A. The letter S means that the total capacity of the shear wall is one of the strongest side only. For more details, refer to Spidwiz or the legend at the bottom of the table. The next term, V, represents the total capacity of the shear wall based on the combination rule and incorporates the perforation factor. V for a wall is the combined shear capacity, and for a shear line is the sum of all wall capacities. Finally, the critical response is the critical design shear force divided by the total capacity of the wall. Of all the terms presented in the table, this is the one which is the most important, as a critical response smaller than 1 represents a shear wall that will not fail. Thus, if the critical response is less than 1, the wall should not fail under the specified design and load settings, and that there is no special warnings at the bottom of the legend. It is always important to verify that there are no warnings at the bottom of a legend for every table. As seen in the critical response column, there is an additional letter besides the critical response ratio. This feature is called the worst case rigid versus flexible diaphragm design, also referred to as envelope design. Essentially, Shearwalls version 10 now compares the walls designed for wind and seismic and selects the wall that has the highest capacity. Therefore, the program compares the walls designed for wind and seismic and selects the wall that has the highest capacity to redistribute forces on the line if deflection is the force criteria. Consequently, the selected wall is also used to redistribute forces to the shear lines for the rigid diaphragm procedure. As a result of the implementation, in the wind design tables, the letter S beside the critical response ratio indicates that the critical case in the design of that wall or wall segment was seismic. Similarly, in the seismic tables, the letter W will be displayed if wind was the critical case for that particular wall or wall segment. Please refer to Tutorial 3, Design Settings for more details. Also, it is possible not to use the results table to find out whether a wall has failed or not, as it is possible to see in the elevation view. And when a wall has failed, failed will be written on the wall. This concludes the end of the tutorial on the wind and seismic shear results. The next tutorial will explain the hold-down design, drag strut forces, deflection, hold-down displacement, and wind section design results table.